we're kind of going to extend what we've been talking about in a way. Don't think of this as like a hard break. Instead, you're going to see several topics as we go through this chapter that we've either already talked about a little bit, maybe in a different light, or I've hinted at a little bit without really going into any detail. All of these things that we've been talking about last chapter, and as soon as we got done with like lenses and that sort of stuff, have all been what we might call modern physics. In other words, there were centuries of Newton's laws. Like we thought we had things figured out, and then we started to figure out light. And by we, I'm just going to go ahead and include myself and all of us in all of these wonderful discoveries. That seem reasonable enough? Yeah, why not? And we had Maxwell and all the people around him that sort of figured all that stuff out. And then all of a sudden, right around the turn of the century, between the 1800s and 1900s, experiments started to be done, and they didn't fit anything. Okay? Like, all of a sudden, it's like, uh-oh, can't explain that. We need some new physics. That's essentially what we've been doing when we talked about some of these interference patterns. When we talked about the double slit experiment, people were like, uh-oh, like I thought light was a wave, but now sometimes it seems to behave like it's not. What are we going to do about that? And as we move into this chapter and what we talk about back in chapter 5, all of this was like new physics at the time, trying to explain experiments that could not be explained with everything they knew, okay? So this starts with what we might consider to be a third way to look at light. We talked about light in terms of waves. We learned about electromagnetic waves. We said, yay, light's a wave. We did a simplification where we just did geometry and pretended light traveled in straight lines, and we used light rays to do a lot of optics work. However, there's a third way we can look at light where we consider that light behaves like tiny particles, like we saw with the double slit experiment when we turn the intensity way down, and it just puts little dots on the screen, like it's just a little packet of light at a time. Those, I'm sure you already know, are called photons, and you can do a lot of work considering light to be little particles, and it will explain a lot of experiments as well. So we start to have these quandaries, right, where it's like kind of depending on which direction you look at things. Like sometimes light behaves like this and fits these theories. Sometimes light behaves like this and fits these theories. They're all correct simultaneously, okay? That maybe causes some problems. It's not really black or white. It's not like light is a wave, except like light is a wave, and it's these other things too. It's all of the above, all right? So we're going to describe this new idea, which is the photon theory of light. This was an idea that Einstein came up with in an attempt to explain some of the new things people were discovering. And he postulated that every one of these photons carried a certain amount of energy given by this equation. So let's say each photon has energy. What is that? Energy. There we go. And I'm going to write this as E sub pH for photon equal to H, a new constant, times the frequency of the light. Each individual photon carries like this packet of energy. So this new constant is known as Planck's constant. Does anybody have Planck's constant memorized? Yeah, you're hitting all around it. 6.626 times 10 to the minus 34 joule seconds. Joule seconds. So joule seconds times frequency, which is 1 over seconds, gives me energy in joules. Also, as we go through this particular chapter, you're going to see overlaps with your chemistry class, things that I'm sure you've learned at some point, or maybe even learned this semester. And hopefully I'm going to give you some physics explanations for some of that stuff that you saw in chemistry, all right? Or you're just going to be like, I already saw this, check out, and that's just going to be the end of it. Drink more coffee. Yes, keep going. Drink the coffee. It'll help, all right? So, photon theory of light, this was an Einstein thing, and we're going to use this experiment, which is a historical experiment that was used and, like Einstein said, do this in an effort to test whether his theory of light as photons was correct, the photoelectric effect. So we're going to describe the experiment and sort of like what how it should behave if light is waves, how it should behave as light is photons, and sort of see which one works and what fits the experiment. But also, I want you to keep in mind, there's a section in the textbook where it says places the photoelectric effect is still used today. I don't have any of those prepared, but there are like common apparati. Is that how you pluralize that one? Yeah, that just sounds bad. Can we just say apparatuses? Yeah, it should be apparati, though, shouldn't it? Why are you laughing? Because I'm wrong? That's right. That was the deal we all made. You laugh when I make a mistake. Where the photoelectric effect is just used commonly. Like a common one would be like doors that open or close based on whether or not you break an invisible beam of light. That's essentially the photoelectric effect that's being used at some point in there using not really this, but more modern pieces of equipment that essentially do the exact same thing. So the photoelectric effect does that sentence right there. If I take metal and expose it to electromagnetic waves specifically above a certain frequency, which, keep in mind, that means that the photons that are incoming have a certain amount of energy. As long as the EM waves are above a certain frequency, then electrons will get emitted by the metal and generate a current. When metal is exposed to EM waves above a certain frequency, electrons are emitted and create a current. You're going to see some terminology here just so you don't get confused. I want to tell you that electrons which are emitted in this fashion, first of all, they're just regular old electrons, but we give them a special name. We call them photoelectrons. They're no different than other electrons. They just happen to get pushed out of the metal using light. Okay, so we call them photoelectrons. This particular type of current we call photocurrent. So if I refer to either of those, just keep in mind that's current and electrons that happen to exist inside the idea of the photoelectric effect in this particular experiment. So let's look over here to the right. And I'm going to change this diagram a little bit because it's not really perfect for what we want to talk about. Yes? It's better if I explain this and then you'll see what they are. Okay? Yeah. Nothing happens. Just nothing happens. It's just like you're just shining light on metal, and that's all that's happening. You can see the metal better, but nothing else interesting occurs. Okay? So the first thing I want to change in this diagram, I want to get rid of this rheostat. We didn't talk about anything. It's just a variable resistor, but it doesn't help us explain things. And I'm going to make a connection there, which really means that this whole entire bottom wire is kind of useless. I don't know why that's there at all. So we all know something about circuit diagrams now. Why is that wire there? I have no idea. Just ignore it, okay? So let me, oh boy, everything here is terrible. So let's ignore that we're calling this an anode and that we're calling that a cathode because they're backwards from the way that I want to talk about it. And let's flip the battery. Why are we even using this diagram? I don't know. And I want the positive side of the battery to be here and the negative there. Okay, so positive, negative, and we're going to connect it. Oop, there we go. Okay, so if this is wired in this fashion, well, all of this over here is connected to the positive side of the battery. So this plate is going to be positive. Okay, so let's say that this is essentially at a higher potential that matches the high potential side of the battery. And everything over on the left is at a lower potential because that's all one conductor over on the left side, kind of like what we did with a capacitor. Okay, so a way to think about that is that the right side of this thing that has all the little E's inside is at a higher potential. It's the positive side. There is no connection. So in between here, it's like, ooh, yay, the wire came to this point, and then I've got like a piece of metal that's here, and then this is all just a vacuum. And over here, I have another piece of metal connected to a wire. So this is an open circuit. There is no connection. There should be no charge flow. Instead, the only thing that should happen is I make a connection to the battery, and I end up with two pieces of metal that, well, they're charged in a way that match the battery. But there should be no current. You'll notice we also have two instruments in here. We have a voltmeter. So first of all, that's just going to allow me to measure the potential difference between this side and this side, which is whatever the potential difference is across the battery, which is the same as the potential difference between the gold and the silver is kind of what it looks like, those two metal plates. So I can monitor the potential difference. But also, if there does happen to be any current flow in the circuit, we've got an ammeter that's in the path that will tell us, right? So we start by just making the connections. We have our little tube that's a vacuum, and the current is zero. The circuit is open. Nothing can flow until we start to shine light. So look at these beautiful light waves. Aren't they nice? Like through the side of this glass tube, through the vacuum, and we shine it on this piece of metal on the left, right? Now, you might imagine we take some light. Maybe we just turn it up to a particular level of brightness or intensity. It turns out that, well, maybe that's going to matter. Maybe it's not. But then maybe we change the frequency of the light. And if you want to think of that as just me changing the color of the light through the visible spectrum, or if we go into the infrared or ultraviolet range, that's possible as well. So we're changing the frequency of the light maybe from some low frequency, and we're going to increase the frequency slowly, right? So if I start at a low frequency, I shine the light on this, I watch the current, no current, no current, no current, no current, which again is no surprise because this is an open circuit. It should not flow. No current, no current, no current. As soon as I reach some frequency, a particular cutoff or threshold frequency, at that point, electrons start to get ejected from this material. In other words, the incident light has enough energy to expel electrons out of this piece of metal. So now all of a sudden it's like, boom, an electron sort of pops out here, and it's like, well, now what do you want me to do? That's an electron. See it? It's like, ooh, what do I do? I don't know where to go. Oh, what should I do? I'm an electron. Well, remember, this is positively charged over here. Well, electrons will be like, oh, I know where to go. And they go over here, and then they can flow through the circuit. Okay? So now I'm measuring a current because I've added enough energy to this metal to pop the electrons out, and I was already supplying a potential difference that would draw any free electrons over to the side. So now we end up with a current in the circuit that should not be there. Electrons are flying through empty space and essentially completing the circuit. Those electrons that do that are what we call photoelectrons. The current that they've made is what we call photocurrent. Again, it's no different than regular current or regular electrons. It's just to specify that they are created in this matter, and that's kind of the end of that story. Okay? Questions?
Is this how solar panels would work?
How solar panels would work? Not exactly. It's close. There's something else like the photovoltaic effect. It's all kind of interrelated and stuff, but not quite. Yes. There's so many, I don't think we're going to run out. Plus also, they're in a loop. So they go around and then they can get ejected again. Yeah. Exactly. We need to draw them somewhere to complete the circuit. Anybody else? Yes. It's the same idea, yeah. If you have enough energy and the electrons, you break their bond and it pops out. It's the same idea, but we're unable to completely observe the effect without putting it in a circuit and seeing what happens. There's a little more going on here that I'm going to tell you about that would, We need to attract them somewhere. Okay? Now, let me look down real quick and make sure I said things I wanted to say about this particular slide. I said that. I said that. I didn't say that. Maybe I should tell you about that. No, not yet. We'll save that for a second. Let's see. I did that. And I didn't do that, but we'll come back to that in a minute. Actually, I do want to say this. So we've got the battery in this particular configuration, okay? And you might imagine it's like an electron gets broken free, and then maybe it's like flying around somewhere, because it's like, I've got all this extra energy. Where do you want me to go? And then we like suck them over to that side, okay? What if electrons are being broken free, but I decide to like say, I don't want to draw you to the other side, instead get back on your metal, okay? And I decide to like exert a force to keep them from even leaving the metal in the first place. So in other words, even if the incident light has enough energy to break them free, it's like they break free and then they get pinned down and they can't go anywhere. The way that I can do that is by reversing this battery, by creating a potential difference in the opposite direction. So imagine that now this is negatively charged and this is positively charged. Now an electron breaks free, and it's like, ooh, if there's enough potential difference here, then all of a sudden they just break free and stay there. Okay? In other words, I have the ability to like completely counteract the effect by setting up a certain potential difference. So let's write that down really quick, and we're going to come back to this in a second. If we reverse the battery, we can stop photoelectrons from leaving. At a certain potential difference. So first, reverse the battery so that we have positives and negatives in the other place. And then we can turn up the voltage, and at some point, we can stop them from going anywhere, even if they have some extra energy as they leave and are trying to fly the other direction. I kind of love the name of this particular potential difference, because it is called the stopping potential. Someone didn't think too long about that one. And we're going to call it delta V sub S. It's a stopping potential difference. It prevents any freed electrons from even moving out into the vacuum at all. It keeps them on the original surface of the first metal. Okay? Yeah.
Do you see the same effect if you put the same circuit but you're shining the light on the other side?
Typically, these are made of two different materials. So we are choosing a certain material that will allow its electrons to go free in this particular arrangement. So maybe the other one is something that doesn't work as well. If you use the exact same metal on both sides, then sure. Yeah. We could be a little more creative with the circuit, or manually would have to do it. Take the battery out and rewire it the opposite direction. It's not you're right, it's not a continuous thing, but imagine that perhaps we disconnect the battery and leave it disconnected, first of all. We could shine the light, and they might have enough energy to free electrons, and they might be doing something like, it's like, ooh, they like get freed. Maybe some of them just sort of end up hanging out right here. Maybe some of them have a little extra energy, and they like fly over this direction. Just imagine there's kind of like a little random sort of spray of electrons that's coming out. But because this is not given a potential difference, they're not going to be drawn this way, so I don't get a current. What we're saying now is that we're going to reconnect the battery, and whatever is kind of free and floating here, we're going to give this enough positive charge that they all get sucked back down that direction. Yeah. Okay. We're almost done with the first slide. I knew this was going to take a while. I'm not surprised at all. Anybody else want to add anything to this? I should give you an equation for the stopping potential. Let's do that. Let's see. So right down here, the stopping potential, delta Vs, is going to be equal to the maximum kinetic energy of any of these free electrons divided by E, the elementary charge, the charge in an electron. Ke max is like the most energetic electrons, the ones that get popped out of the metal and then like have all this extra energy to spare because kinetic energy is related to velocity, so they're the ones that fly off with the most extra energy. We want to have enough potential to stop even the ones that are most energetic. So this is going to stop everything, and of course ones that have less energy, they're easily going to be stopped because, well, they don't have as much energy as the more energetic ones, all right? Let me tie a few things together by giving you some additional equations. So, how much energy does a photon have to expel an electron? So to produce a single photoelectron, let's think about what has to happen with the incoming photon. And you can see I've sort of written out the equation there for you, thinking about the different steps. The first thing that has to happen is there has to be enough energy to free the electron. It's bound inside of its atom to its nucleus. So we first of all have to get it free, all right? The next thing is there has to be enough energy to get that electron to the surface of the material. So maybe it's buried way down in there and all of a sudden, like it gets hit with a photon, it's like, boom, I got knocked free. Well, that's not enough to give me a photoelectron because now, like, somehow we need to, like, fight through all the other atoms to get to the surface before it can go anywhere. That's going to take some energy. And then finally, at the end, maybe there's some energy left over, maybe there's not. But you add to that whatever kinetic energy is left over as it goes flying out of the material. Those three things added together tells you how much energy the incoming photon had that originally set that photoelectron free. Okay? So maybe we draw a little picture here. Here's our metal. And somewhere in here is an electron. Whee! There we go. So first of all, it's hanging out around, in its own atom. So first of all, we have to go, boom, and break it free. So now it's out here. And then that electron has to get to the surface. And then maybe it goes flying off with some velocity and has kinetic energy. So the photon hits and gives up all of its energy, and it's going to go into these three places as the electron flies off. Yeah. Yeah. So, yeah, it depends on everything about the material. Okay? So this first thing here, the energy to break the electron free, has a name in and of itself. This is called sadly, the work function of the material. The amount of energy that's required to break the electron free from that given metal is known as the work function of the material. So depending on what you use, gold, silver, whatever other metal it is, you can look at a table in the book. They all have different numbers that describe basically how strongly those electrons are bound originally, and they tell you how much energy is required to break that electron free. Let's see. Let's add to this here at the bottom. Which photoelectrons are going to have the most kinetic energy left over? It would make sense that they're the ones that don't have to do this middle part. Okay? So if they're already like in their atom bound and they happen to be in an atom that's like right at the surface, they don't have to do the step of fighting their way to the surface. In other words, they get free and go flying off with whatever extra energy they were given by the photon. So the ones that have the most kinetic energy, or Ke max, will be the ones that are right on the surface of the material, which means we can write an equation that says this. The energy of the photon is equal to the work function of the material plus Ke max. This is essentially this equation at the top, just with the middle term removed. This describes the ones that have the most energy because we're leaving out that middle term. If we were dealing with electrons that were buried down deep in there somewhere, well, then we would have the work function plus some unknown something. I don't know how much energy is required to get to the surface, plus kinetic energy, but it wouldn't be the maximum kinetic energy. It would just be Ke. Okay? In that case, we would have just, exactly what's described there. Okay? It wouldn't be the maximum. It would just be however much energy is left over. Let me see if there's anything I need to put with this. Oh. Actually, let's rearrange this equation, because I think if we write it the other way, it kind of makes sense. The maximum kinetic energy that any of the electrons have is equal to the energy of the photon minus the work function. Read that equation and think about it just a little bit. The electrons that have the most leftover energy to fly away with are going to have energy equal to the amount of energy the photon had coming in minus however much energy was required to break it free. That seems to fit, okay? The only place energy was lost was in breaking it free. So I think we've got everything we need to say there, and I've got just enough time to give you this third slide, even though it has a lot of words on it, and then we'll be done at a good breaking place for Monday, okay? So first of all, at the top, what is wave theory? If we assume light is a wave, what would be its assumptions? What would we expect to happen here? We would first of all think that, well, if I just make the light brighter, it would make sense that I would eject more electrons and they would have more kinetic energy. Because really what we're saying here, if it has more intensity, then the electric field in there has a bigger amplitude, which means it's going to exert a greater force on those electrons. Turns out that that doesn't happen at all, okay? So we don't get this extra kinetic energy, and that doesn't happen, so there's an X against that one. Also, changing the frequency, we wouldn't expect to change the kinetic energy at all. And it turns out that the frequency does affect the kinetic energy of electrons, so this one fails. And then finally, you would sort of expect that if I turn the light way down low, maybe we would still get an effect just because, like, the incoming photons, each one would give up a little bit of energy, and eventually maybe there would be enough energy to break an electron free. But that doesn't happen at all. They never break free, even if you wait a period of time. The thing that matters is that they have to have enough incoming energy. It's not about the intensity, it's about the frequency of the incoming light. So this one also doesn't happen. It turns out these predictions of photon theory, all four of these happen exactly as described. If I turn up the intensity, we get more incoming photons, and we get more photoelectrons. It just turns out that their maximum kinetic energy isn't changed, which you see as number 2. So as I turn up the intensity, kinetic energy that they have is the kinetic energy they have because, well, I haven't changed the frequency. The energy of each incoming photon is unchanged, so that doesn't matter. Once we get to these last two, we can see these graphs here at the bottom. Notice it says the maximum kinetic energy should increase linearly with the frequency of light. And if you ignore these little parts down here, which really don't relate to us, you can see that if I have too low a frequency, I get zero kinetic energy, like there's no electrons that come out at all. And then all of a sudden, it's like, ooh, as I increase the frequency further, my electrons that are emitted have more and more kinetic energy. And that's exactly what happens experimentally. But then finally, you'll notice over here on the left, they tried 2 different intensities of light, and it turns out you get more electrons and more current if I increase the intensity, but they have the exact same kinetic energy because both of them require the exact same stopping potential to get nothing to happen. And you may remember that if I go back 2 slides, the stopping potential is directly related to the kinetic energy. So they have the same kinetic energy, but you get more current. We are out of time. I wish I had a little more. Read through these. If something doesn't quite add up or make sense, let me know. And also, let me just warn you, our textbook is bad at this particular topic. It might help to find a video online or read something in another textbook, because I read through it and I was like, ugh, convoluted. I checked another textbook and I was like, aha, that's perfectly clear and nice, all right? So that's the end of the week. Yay. Goodbye. Drink an extra. All right, at the end of last week, we had a bit of a mess. My whole explanation of this slide was just awful. Okay? I completely and totally admit that. I was in a rush. I tried to do it in 3 minutes. I said a bunch of things, and I'm like, I don't even know what I said. So, in an effort to redo this slide, if you look at the start of our 6B slides, we have a reworked version of this slide that I'm going to go through, and then we'll go back to the 6A slides. Okay? I think that this is better organization of the material instead of just like a bunch of text that was up there that I was reading through. And hopefully you'll have a better understanding of why the photoelectric effect fits photon theory and seems to prove the existence of light particles and completely disagrees with wave theory, even though other experiments tell us light is a wave. Okay? So before we do this, does anybody have any questions about the photoelectric effect as a whole, now that you've had a chance to look at the experiment? Do you get what's happening? Like if you go back to, I don't think you looked at the experiment, unless you have a home lab and decided to set this up over the weekend. Nobody did, I don't think. Maybe you did? No, okay. Are there any questions about this? There seems to be more of you here today. Yes? What's up with that? Where'd the rest of you come from? Where have you been? Okay, I'm going to ask a question. Be honest if you want to be, I guess. There's no penalties to answering this question truthfully. In the last, let's say, 3 weeks, 9 classes, how many of you here today haven't been here? Ooh. How many of you have been here, say, less than a third of those? 3 or less? Okay, so where have you been? Why come back today? The weather's nice? Huh? You recovered? You've all been sick? Sick with life? You just had enough of the semester? And okay. Huh, weird. I don't know what's going on. So this experiment, light shines on metal. If the light has the right conditions, it'll eject electrons that we call photoelectrons out. Those are attracted by a potential difference over to the right, and then that essentially completes what would be an open circuit, and we see a current that we call a photocurrent. Okay? Now, let's go back. Ooh, there's the slide that was bad. Let me hop over here. And let's talk about these 3 things on the left and how those 3 things would be expected to affect the experiment if the light was waves, and how we would expect it to affect the experiment if the light is made up of photons. So you can see the first one there. If I turn up the light, increasing intensity, as I turn it up and the light gets brighter and brighter and brighter, you can just think of that as the light perhaps having more energy in that beam as a whole. That could be shown in the wave theory as just like bigger amplitude, okay? So we would expect there to be a higher ejection of photoelectrons. I'm putting more energy in. It makes sense that more get kicked out. That's true whether I consider photons or wave theory. In both cases, we would expect more photoelectrons, and that would be reflected in how much current we measure, okay? The thing that's different as I increase the intensity is we would expect that, if I'm just putting more energy in, then in those electrons that I've ejected, we would expect whatever the ones that are the most energetic are to have more energy. I put more energy in, they should all have more energy, okay? But that doesn't work in the case of photon theory. Instead, remember, we have an equation for how much energy is in each photon. So if I turn up the intensity, I'm not actually putting in more energy. I've just got more photons, each of which still have the exact same amount of energy. So the sum total is more energy, but I haven't increased the energy in each individual particle. Hello, more people behind me. Seriously, where is everyone coming from today? This is just weird, all right? So in the case of photon theory, well, since the individual photons don't have more energy, we don't necessarily necessarily expect the individual electrons that got ejected to have more energy. Do you see the difference there? Okay? In one case, it's just like, blah, more energy is hitting because the waves are higher, so we expect everything that comes out to be more energetic. In the second case, there's more energy as a bulk, but each individual particle doesn't have more energy. Therefore, the things that get ejected don't have any more energy than before. All right? When I look at the experiment, take a look and connect these things down to this graph. There are two graphs. The intensity. We've gone from low to high intensity. You'll notice this is a graph of photocurrent, so we are actually getting more current. So it's like, yay, that checks and that checks. We are getting more current with more intensity. But you might remember this thing called the stopping potential. It's the amount that I can reverse the potential difference and turn it up in an effort to keep the photoelectrons on there. Not let them leave, to stop them with potential. You might remember there was an equation that related this to the maximum kinetic energy. It is equal to E times the stopping potential. So it's directly related to how much kinetic energy the most energetic photoelectrons have. Notice it goes back to the exact same point. Even if I turn up the intensity, it takes the exact same amount of stopping potential to stop them, to keep them on the original metal. Which means that I have increased the current, but I haven't increased the amount of kinetic energy of the individual electrons. That fits photon theory, but completely breaks with what we would expect if it was a wave. All right? Let me pause there. That's number one. Ask your questions. Yes?
How do you read the chart?
Which chart where? That one?
Well, the top one says more photoelectrons and then the higher kinetic energy max compared to the right side. Is there one wrong and one correct?
It works out experimentally that things could be correct or incorrect. In this particular case, the 3 check marks are verified, but that one X didn't work out.
So that means it's not wave.
So it must not be wave based on that first part. Okay? Someone else. I'm just going to wait a minute because I know you can get lost in this. Yeah.
So the thinking is that since it's like even at different intensities, we still have the same relative to the stopping potential. There's no like change in kinetic energy.
That's correct. So if this is the same for both, then that must be the same. Who else? No. Number 2. Okay, number 2. What happens with frequency? If I turn up the frequency, or even if I just go to different frequencies of incoming light, what do we expect? Well, for wave theory, frequency shouldn't matter. It's like I'm putting some energy in. If I put energy in, it should kick some electrons out. That's just how it should work. Even if it takes a while, eventually there should be enough energy to go in there that some electrons come out. Well, it turns out that this doesn't happen. Okay? Instead, for photon theory, we expect there to be a cutoff frequency. Only if the frequency of the incoming light is high enough does anything happen. Below that frequency, it's just nothing. There's no activity at all. The circuit's open. As soon as I hit that frequency, current begins to happen because electrons are ejected. Okay? Look at this experiment down below here. And again, you can ignore this part. We're not using that symbol exactly. And here we're looking at the kinetic energy of the most energetic photoelectrons, Ke max, as a function of frequency. Just take a look at the green line. So for one example metal, I like that, metal 1. Who knows? Some kind of metal. Doesn't really matter. You can see that if I start at 0 frequency and begin to go to higher frequencies, like all of this region, like nothing's happening. No electrons are being ejected until I reach this particular frequency, at which all of a sudden there's activity. Electrons are coming out, stuff is happening. I hit the cutoff frequency, and now the photoelectric effect takes over. That happens no matter what the metal is. It may have a different cutoff frequency because it may have its electrons bonded more tightly. But in all cases, there is a particular frequency below which nothing happens at all. So photoelectrons are only for only high enough frequencies. Having trouble reading my own writing there, all right? On the other hand, we would expect from wave theory, if I turn up the frequency, to just not be involved at all. It shouldn't matter how much energy the electrons have. And instead, for photon theory, we expect a linear increase, which is reflected in this graph. As I increase the frequency, the kinetic energy of those photoelectrons goes up linearly, okay? So it fits this, but it doesn't show zero effect. And then finally, for intensity. If the intensity is really, really low, maybe it's so low that we wouldn't expect really anything to happen in any case immediately. But if I wait long enough, you would expect there to be enough incoming light that eventually maybe, one electron's like, fine, that's enough energy, I'll leave, and then it gets pushed out and off it goes. You would expect if you wait long enough, eventually you would have photoelectrons no matter what the frequency is. But it doesn't matter. If I'm down in this regime such that my frequency is too low, you can sit there for eternity with that incoming light, and never is an electron going to leave. It's just not going to happen. With photon theory, we expect as long as you're above this certain frequency, it doesn't really matter how low the intensity is. As long as there's some light that has at least one photon with that frequency, that can kick out one electron, okay? So looking at the results, this works and that doesn't work. So if you just wanted to count the score, well, even though wave theory got 1, it lost overall. This particular experiment seems to say that light is made up of little particles. It's only because we have other experiments where we saw the wave nature dealing with interference and diffraction that we can continue to say, no, but it's a wave. Both are true, okay? Who's got questions about the photoelectric effect before we leave it for something else? Yeah. Mm-hmm. What's that again? Why does it plateau? Oh, let's see. So we have a photocurrent versus potential difference. At some point, it's not about the potential difference I'm applying. We're just using it to, say, attract the electrons to one plate. It's the light that's making them leave. So the amount of current that you get is all about how many photons are coming in, not about what I'm using to collect them. So it's going to reach some maximum value that's completely independent of potential difference. Who else? Yes. What's on the left? So you're talking about this little region, okay? So everything on this side is when I have the experiment set up as originally planned. I make the one side positive to draw the electrons to it. Everything on the left is when I've flipped the battery, and now I'm starting to increase the negative potential difference, and I keep increasing it until I've managed to push all of them back to decrease the current to zero. Okay? More? Anybody? Anything? I know there will be more questions later. People will have questions. All right. I'm going to leave this for now, go back to 6A, and go to the next slide. All right? I'm hoping that in the next few slides, we're going to make a connection between things that you've seen in chemistry classes and maybe even high school chemistry classes for a long time that perhaps you didn't see as having a physics connection. We're going to try to make a connection with a lot of things that, well, we've learned about last semester and this semester, with maybe some rules that you just accepted from a chemistry class. So first of all, to explain any of this, let me show you something that I bet most of you have seen, and that is atomic spectra. If I take a low-pressure gas and put it like I don't know, think of it maybe in a contained tube, and then I heat it up. At some point, I can look at that and see that it emits only very specific wavelengths of light. Not a continuous spectrum of light, but rather just specific wavelengths. We would have to use maybe something like the diffraction grating example that I showed you before to split out those different wavelengths so they're not all just merged. And you can see something like what you see there in the case of hydrogen, which is going to be the element that we focus on entirely for the next few slides. Notice, at least in the visible spectrum, you see those particular 4 wavelengths of light, or 4 colors. There are others in the infrared and ultraviolet range as well, which we'll see on the next slide. The opposite happens as well. If I pass all the wavelengths of light through this gas, you will see black lines where there's missing colors. It absorbs the same wavelengths of light that it emitted. Emission spectrum and absorption spectrum. Okay? You can think of this as essentially a fingerprint if you want to. And I think it would be wrong if I didn't put quotes around that. That would be almost like saying this is literally the print on the finger of an atom. And that's just not true, and that would be weird. You can think of this as the fingerprint for an atom. In other words, it helps you identify what it is. It's unique for each individual atom. So if we're going to do anything with a model of the atom, and if our model of the atom is going to make any sense, it has to explain this. And it has to explain it in both cases, and it needs to even predict exactly what frequencies or wavelengths of light are going to be emitted. Okay? So if we were to zoom in on that just a little bit more, your spectrum of hydrogen looks something like this. The visible ones we just saw are right there. And as you can see, there are many more of these. Is this familiar to anyone? Raise your hand. It's familiar to more of you, I think. You just don't want to raise your hand. You've seen it. Many of you have seen it. At least half of you, it looks like, have seen it. These different emission lines for hydrogen fit the 3 equations that you see there, and just from historical reasons, they are given these 3 names because they break up into sort of 3 rough groups. This only works for hydrogen, and it turns out that trying to define such rules for even one step up in element, all of a sudden you've got problems and none of this works. Okay, so we're going to have to focus on hydrogen only. So you can see 3 equations there that relate the wavelength of the emission line to a few other things here. So this is a constant, the Rydberg constant, or G, and let me make sure I get the right number, because it's not a constant I use often. Where is it? Maybe one of you can quote it. Go. Maybe not. Yeah, there's like 3 of you who are like, it just ran through your head, and you're like, I don't want to be that geek who says the number, but it's okay. All right, fine. 1.0974 times 10 to the 7th, and that's in inverse meters. So we put that constant in, and then you can see the only other thing in there is n. We plug in n starting with 2 and going up, and it'll predict all of these lines that are in the Lyman series. As you move over to the Balmer and the Paschen series, you can see the only difference really is that we are starting with a different number here, and also where we start n is going up by 1. So we could combine all of these and write a slightly more general equation that looks like this. 1 over lambda equals r times 1 over, and I love the superscript, n prime squared. You got to hate that. I tried to keep them separate so it doesn't look like a 12. Minus 1 over n squared. And we could say that n is equal to n prime plus 1 to infinity. And, of course, n prime there is just going to be 1, 2, or 3, depending on which series you're talking about. Now, we say this is a general equation, again, just for hydrogen. It's quite limiting, actually. This is just more of an empirical rule. It's just like, this describes the lines that we observe experimentally. However, keep this equation in mind because we're going to see it again, although I probably won't quite get to the derivation today. It'll probably happen Wednesday. I want to also show you how we can get from not just showing you this, but using some physical principles that we've learned about to get to the exact same equation. So, before we can get to that, we're going to talk about the Bohr model of the hydrogen atom. Who knows anything about the Bohr model? A few of you? Who's had chemistry in college thus far? All of you, perhaps, I hope at this point? Okay. Did you talk about the Bohr model? Then why did only like 2 of you raise your hand? It's like, did I have chemistry? Yeah. You did it a little bit? Just a little bit. You did this a lot? No, just a little bit? I'm trying to figure out what you people learn elsewhere. I have no idea. Because sometimes, I talk about things and I assume that you know nothing about it when you actually do. And sometimes it's the other way around. And it's hard to get it right because unless I come to all your other classes, who knows? No, I don't have time. No, I don't have time for that. No, just no. All right, the Bohr model of the hydrogen atom. So first of all, the spectra stuff came up. There was a previous Rutherford model of the atom, and it didn't work. It had no explanation at all when people did these experiments and saw these spectral lines, nothing at all. It turns out that Bohr was actually someone who worked underneath Rutherford and decided to upend him, I guess. He's like, ooh, I can explain it, and came up with his own model. I wonder how that felt for Rutherford. You think he was proud, or do you think he was a little upset? A little bit of both? He probably had some mixed feelings, like, ooh, he's explaining like the world better than I am. But alas, no one's going to use the Rutherford model anymore. That's just sad all around. So, I don't know. He was happy, maybe he wasn't. So Bohr tried to explain the spectral lines, and also at the same time, the idea of quantum physics was sort of cropping up a little bit. And he tried to incorporate some of those exact same ideas. We are not going to have time in this class to do like days of quantum physics. However, I would like to do like half a lecture, maybe. Okay, like nothing that would be on the exam. Rather just, see, if I don't tell you when it is, then maybe you'll come, even though I'm not talking about something that'll be on the exam. But just enough so you're like, oh, someone brought up quantum physics. I kind of know what that is without being able to like actually do any of it. Okay, I think it's useful to understand some of the ideas. So hopefully we'll get to that maybe Friday if everything works out. Oh, I just told you. Could be Monday. Could be Wednesday. You never know. All right. So I have to point out as well that poor Bohr, he lost out as well. Like, this is useful to us because there's a lot of sort of historical hangovers in the terminology that you still use in physics and chemistry and elsewhere. And also, it's a model that does explain several things and helps us understand atomic physics and chemistry somewhat. It's just not perfect. It's nowhere near perfect. It's been superseded by other better theories and models in the interim years. So, how does the Bohr model start out? And let me go ahead and warn you. I'm going to list some other facts here, and then we're going to do a lot of equations for a very long time. Like, there's going to be one big topic probably for this slide, this one that's blank, and if I'm right, I'm probably going to have to insert one. So I don't know what it takes mentally for you to be like, oh, I need my attention span, like to be big and broad. If you need to take deep breaths, have a drink. If you need extra caffeine, I'm going to try to make it as interesting as possible, but I understand I could lose some of you halfway through. Let me also just point out, none of it's hard, okay? I promise you none of it's hard. So it's not going to be like a real head scratcher where like there's a whole page of work with a step that I skipped somewhere. Don't you love it when textbooks do that? You're like, I wouldn't know. I never figure out what's in between the steps in my textbook. If you've ever, anybody? Yeah, it's like equation 12-12 is easily replaced by 12-13, but they don't tell you there's like a textbook hiding inside there until you try to do it yourself. And you're like, yeah, that was terrible. So bear with me as we work through the Bohr model, applying some basic physics that we've learned over 2 semesters. You don't look as ready as I feel. I'm wondering how many of you haven't been here in the last 3 weeks are thinking like, why did I come today? Why did this happen? All right, so first of all, I need to add a few points to this that I really should have included right at the top, but I didn't prepare my notes at the time, so I need to tell you this now. So we're going to say, first of all, there are only certain allowed circular orbits for the electrons. In other words, as you might expect, Bohr imagined it almost like a little planetary system, which we now know is completely inaccurate, but still works for a lot of different things. Only certain allowed circular orbits for electrons. It can't just orbit the nucleus at any distance. There's specific places where it works. These orbits were called stationary states. Why are they called stationary states when they're orbiting? Good question. Just accept it. It'll be fine. Number 2, we are going to say that an electron in a given orbit has a specific energy. And if you want, think of these as sort of Bohr's starting assumptions, the way he's building his model. Number 3, this was a leap. Number 4, no, I should tell you what number 3 is. Although it'd be funny if we just left it like that. Number 3, Bohr just, like, there you go. And then he hoped that would help him out somehow. So he said that electrons don't radiate energy while orbiting. We talked about electromagnetic waves and how they're created. If you understood a little bit from that chapter, there should be something about this statement that bothers you. How did we make electromagnetic waves? Acceleration, right? We took like the electrons and like an antenna and accelerated them up and down while they were moving. That resulted in the radiation away from that of an electromagnetic wave. He's saying that even while they're in these orbits, that's not happening. This is a bit of a problem. Okay, so he's kind of stepping into left field here a little bit, trying to build this theory while stepping away from what was known at the time. If you think about an electron moving in a circular orbit, it's accelerating, right? Centripetal acceleration from last semester. It's changing its velocity direction. That is accelerating, which means you should get EM waves, but he's going to hypothesize that it doesn't happen. Why? Because if it does, then the electron, by conservation of energy, is going to lose some energy. If it's like radiating some energy away while it orbits, well, then it's losing energy as it orbits, and eventually it'll just like orbit its way right into the nucleus. And that doesn't happen. So I guess he's got some footing there a little bit. Like, that doesn't happen, therefore maybe this is okay, all right? So there's a physical reason to say this, but we should put a little note here that this violates the previous understanding of how things worked. It violates what they knew at the time, and it violates what we've learned in this class. Ouch. Okay? And number 4, finally, we're going to get to an equation. Once we have these things in place, the basic idea was perhaps exactly what you learned in chemistry class. An electron moving from a high energy state emits a photon. If an electron changes state, in other words, it's changing its orbit from one particular energy to another, and it's going from high to low, that energy has to go somewhere, and Bohr speculates that results in a photon being emitted, which is going to try to explain these emission spectra. Okay? This we could represent as an equation. What was the equation for the energy of a photon? HF. I heard HF at the exact same time I heard finally some pages turning. Like, it's in here somewhere. I'll find it. HF. So we could say that the energy of the photon is HF, the Planck's constant, times the frequency. And now we're going to say that the energy of that photon is equal to the energy of the upper energy state minus the energy of the lower energy state. All right, good so far? Everybody still okay? We have so much further to go. We're not going to finish this today. Question? Say again? That photon is basically being generated by conservation of energy. Something caused the electron to spontaneously perhaps move into a lower state. And now I have to say that this new energy that the photon has, plus the new energy of my electron, has to equal the energy that it had before. Yes, it's a bit of a leap, because we have no explanation for the mechanism why this would happen, just nothing at all. Bohr's just putting things together to try to explain the spectral lines while leaving some things out, for sure. Okay? All right. Now, at this point, Bohr just comes up with an equation. Are you ready for this one? All right. So he assumed a couple of different things. So first of all, he assumed the electron's angular momentum was quantized. Angular momentum, we learned about last semester. It was really everyone's favorite, if I recall correctly. You all loved angular momentum. Yeah, just nod. Just nod. Nod. Nod is up and down. Shake is this way. Don't shake, nod. Not snap. It was, did I say nap? I think I did. Anytime you snap, there's a little bit of a nap in there. No, I don't think so. So what does this mean? Quantized. Quantized means that the angular momentum can only have certain values. Any value of angular momentum is not allowed. And he said that these allowed values were equal to this. And this is a completely made-up equation that just fit with the equations that were already there and gave him the answer he wanted. Almost like maybe what you do sometimes with homework, right? Like you know the answer you're looking for, either because your friend got it or you looked up the answer online, and you know the question. So you're just like, well, if I do that in the middle, I can like reverse engineer this. I don't know why I did it, but that's what I did. Who has done this? I will readily admit that was grad school. Like so much of that, just trying to put pieces together and figure out what was going on. So here is Bohr's angular momentum equation. He said that the angular momentum that was allowed for the electron was equal to n times h, Planck's constant, over 2 pi. This is Bohr's quantum condition. Okay? So we said at the start that he was going to try to incorporate some of the new ideas of quantum physics at the time. So he has a value that in his equations are going to be quantized. So this is his condition that fit the equations and the spectral lines and simultaneously involved quantum ideas. Yeah. What's n? N is just an integer. So we'll say n is equal to 1, 2, 3, up to as many as you want. And you've probably seen this exact same n before as the principal That's not it. That's Princeps, I think. Now, let's try that again. Quantum number. Anybody remember the principal quantum number before from a chemistry class? Yeah, there's like a series of quantum numbers, and they have certain rules and stuff. That's where some of this stuff is starting with, Bohr's quantum condition. Only certain allowed values of angular momentum. So let's connect this with what we learned about angular momentum last semester. So next slide. Does anybody happen to remember the equation for angular momentum? I made a joke, I think. You're not going to remember the equation for angular momentum. Or you might? No, that's the new one. What's the old one? What if I had like a disk that was rotating at a certain angular velocity? Something times something. What was that? I think you're about to say it. Ooh, there it is. I times angular velocity. I omega. Yeah. That is in the data that you flushed from your brain at the end of last semester. So let's see. I omega. If we're dealing with an electron, you can think of that as just a point mass that's going around some axis of rotation. What was the moment of inertia for that? Yeah? For a point mass. And that basically fits what the electron is. It's a tiny little mass that's moving around some axis of rotation, which would be the nucleus in this case. Omega. Does anybody remember how to relate the angular velocity back to the linear velocity? I like how you're all like, it's in your brain somewhere and you really want to remember, don't you? Yes. All the answers are coming right here, just very quietly. It's omega is V over R. V is R omega. Who said? I didn't, right? Somebody back there said it too, apparently. Yeah, good job. Okay. So, let's see. We can simplify that a little bit. That's just going to be MVR. And now we're going to set that equal to this new equation, which is NH over 2 pi. And since different orbits will have a different radius, and each one of those has a different angular momentum or energy, this n, which is our principal quantum number, n equals 1, 2, 3, and so forth, corresponds to different radii. So I'm going to put a subscript n on the radius. So if it helps, maybe think of that as the nth orbit radius. So let's see. What do we have at this point? This is our angular momentum condition. And let me just make a point that this worked and fit experiments that were being done at the time. However, there were assumptions that were made, and there wasn't a lot of physical reason behind some of the assumptions. In other words, the theory behind why he did this was weak, okay? So we have something at this point that just putting this thing together predicted the different energies and the orbits and the spectral lines, but the theory was weak. We are going to try to fill in some of that theory a little bit. There we go. So, let's just look at what we have. We have an electron in a circular orbit with a centripetal acceleration. And that electron is attracted to a positive nucleus. We're going to put those two ideas together. We learned about the second one there this semester. We know something about the attractive force between charges, positive and negative. We know something about circular orbits based on last semester, or maybe I'll remind you of what you knew about it last semester, okay? So let's see. Let's start with the second part. Let's say that the electric force is equal to what? Coulomb's law. Do you remember it? You need to. Yeah. K Q1 Q2 over R squared. This describes the attraction between the positive nucleus and one electron, which we can rewrite as 1 over 4 pi epsilon naught for K, and I'm doing that for later reasons, which you'll see some stuff will cancel out. And I have two different charges. I've got an electron and I've got a nucleus that may have multiple positive charges in it. So we're going to write it like this. We will say Q1 is the nucleus. We're going to let it be Z times E, the elementary charge. And the electron just has elementary charge E. We're taking the magnitude, so don't worry about the negative sign there. And that's all over R squared, but we're specifically talking about one of the orbits that we could give the label R sub n. That's a Z. Why Z? I'll put it here. Let's see. So this is the electron. This thing is for the nucleus. And we will say that Z is equal to the number of protons in the nucleus. Of course, Z is just equal to 1 if we're dealing with hydrogen, but we're leaving it a little more general right now. This attraction is still there, even if it's moving. There's just more complications that are involved. Think of it as they're staying a fixed distance apart. So even though it has motion that's circular, R is staying constant. So it's a good approximation. Good question. Okay, so this describes the attractive force between the electron and the nucleus. Are we still okay? Yes, question. It all depends on the nucleus of which atom we're talking about. There's going to be some number of positive charges mixed with neutrons as well, but the overall net positive charge in the nucleus will be equal to the elementary charge, which each proton has, times the number of protons that are there. E is the amount of charge on each proton. Our elementary charge, 1.602. Are there more digits than that? Times 10 to the minus 19. But after the 2, there's more probably, but who knows, all right? So let's keep going. Let me make a little note over here as well. Z is equal to 1 for hydrogen, but we're going to leave it like this is for now. We're going to come back and narrow this down for hydrogen in just a little bit. So this describes this the second part of the statement. Ooh, I think I'm going to highlight that a little bit. So this goes with this. Ooh, things are getting fancy today. You like this color? It's too dark? Is that better? That's much better? Look, it looks nothing like the projector. Horrible projector color matching. Now I'm upset. We need a new projector. Look, isn't that just the worst? So let's go look at this centripetal acceleration. We're going to make the assumption that the only force that's acting on the electron is this force. We're going to ignore any gravity. It's going to be negligible by comparison. So we could do this and say, ooh, everyone's going to love this. The sum of the forces in the C direction. Remember, the C direction is toward the center of the circular motion, so towards the nucleus in this case is equal to mass times acceleration in the C direction. That AC is our centripetal acceleration, and the sum of forces is just the force we have above. So let's write that down. Let's see. So now I've got 1 over 4 pi epsilon naught ZE squared over RN squared. And what is the centripetal acceleration? Anybody remember? Yeah, there you go. V squared over R. So that first point, let's pick a different color for that one. Let's go with this. So in circular orbit with centripetal acceleration goes with this. Okay? Any questions? Something's happening in the hall. think we're about to get raided or something. It's very loud out there. They all want to come hear me speak, don't they? That's what, yeah, I'm sure that's what it is. Yeah, no, not at all. All right, any questions about what we have there so far? We good? Let's simplify this and solve for the radius, and that's going to be my dropping off point for the day. So let's say, let's solve this for Rn. So one of those cancels out with that one. What? For who? What? Oh, you can't read the terrible handwriting? For R sub n. There we go. So let's see. We've got Rn is going to be equal to Z e squared over 4 pi epsilon naught m v squared. I don't know, but I think we're done for the day. It would seem that way at least. Did I include everything there? For that. So what did we do here so far? Let's see. We are talking about the Bohr model of the hydrogen atom, and we've worked through a few different basic physics ideas that span the course of our 2 semesters as we've started putting this idea together. Just to mark those, let's see. We have something here about angular momentum. So there's a last semester topic. We've got this sort of ridiculous made-up equation that Bohr just used because it worked. It fit in the equation to give him the answer that he wanted. That's not the way you're really supposed to do science in general, but, you know, sometimes it pans out, as we'll see later in today's lecture. We put that together also with the angular momentum equation we had last semester. We used that, and a little bit of moment of inertia in there as well. Then from this semester, we used Coulomb's law, and then Newton's second law and circular motion. So a lot of stuff, random seeming things that we've learned about have gone into this so far, and that's not the end of it, okay? So before we were somewhat rudely interrupted at the end of the last class, I don't know what all that was about, but alas. I think, you know, as it approaches 4 o'clock, we should really, like, chain the doors or something, you know? Or at least, you know, if anyone tries to come in, we should have assigned people that, like, rush the door and say, no, don't enter until 4 o'clock. But you're actually thinking, like, well, if they come in, he may quit and run him out, and then that'll be okay? I don't know. We'll see what happens. I have no idea if something is happening at 4 today. So let's see. We made it as far as getting this equation for the different radii of circular orbits. We weren't quite done with that, though, it turns out. Let me see if I can find the right place in my notes. That is not that equation. It's that one, okay? So into this, we are going to make 2 substitutions. So first of all, we're going to use the equation all the way at the top. So let's draw a circle around that. We're going to use, which part of it? This. And we're going to bring it down here. And we are going to solve it for v. So let's solve that for velocity. That's going to give me nh over m rn 2 pi. And we're going to plug that in for velocity in the boxed equation. So that's one substitution we're going to make. And I thought there was a second substitution, but apparently I'm wrong as I'm looking at my notes. It says, and from above that, solve for velocity. Okay, so let's plug that in and do a little bit of algebra all together. Are you ready? So into the denominator, square it. A bunch of stuff happens. Do you want to do the steps or just me tell you what it is? Yeah, okay, so some stuff cancels out, and you should end up with this. You get Rn is equal to epsilon naught n squared h squared over z e squared pi m. What a mess that is. This is the radii of all possible orbits. The ones that are allowed. And don't forget that n is equal to 1, 2, 3, and so forth. Integers, starting with 1. So it turns out the smallest orbit that's possible is going to be for hydrogen, which means we're going to have n equal to 1 and also z, the number of protons in the nucleus, equal to 1. So let's add a slide. We need some room. We'll use that. And we're going to plug in z equals 1 and r equals 1. Do you need the previous slide again? No. Smallest possible orbit, z equals 1, and r equals 1. And then you can plug in the rest of those numbers. So let's see. I'm going to go ahead and write this out just to make sure we're all on the same page. So we're going to have epsilon naught, so that's 8.85 times 10 to the minus 12. Then I think that's a set of n squared in the numerator. So we've got 1 squared, and then we've got 8 squared, which is Planck's constant, 6.626 times 10 to the minus 34. And then in the denominator, we've got 1 for z. E is the elementary charge. There's a pi down there. Ooh, pi. And the mass of the electron, which is 9.11 times 10 to the minus 31. It's the thing that's orbiting. And once you do all of that, you should get 0.529 times 10 to the minus 10 meters, which is also known as the Bohr radius. The smallest possible radius for an electron in any of the atoms. Okay? Your question? 31. I think that's a 31. Should be a 31. It's a 31, although it looks like a J1 a little bit. It's a little better. So let's do this. As a little simplification, we could say, let's let Rn be equal to n squared over z. So the two things that we plugged in values for. And then we have all of those other constants. Keep in mind for what we just did, this is 1, which means that all of the other constants multiplied together are this Bohr radius thing. So that's going to be R1. And if we do that, then we can say that R2 is going to be 4 times R1, and R3 is going to be 9 times R1, and you get the idea. We're going to get Rn is n squared R1 for hydrogen. Numbers you've probably seen floated around before. Yeah.
Why is it just for hydrogen?
For all of this, we're plugging in z equal to 1. So 1 proton in the nucleus. This is only going to work for hydrogen. There it is. There's a lot of staring. I was like, scaring me. Okay? If we want to go for other elements, we could say that in general for z not equal to 1, we could write that Rn is equal to n squared over z times that Bohr radius value, 0.529 times 10 to the minus 10 meters. Which finishes the part about allowed orbits. Certain distances that electrons can orbit around a nucleus. Questions about anything that's up there or that we've talked about today before we jump into talking about the energies of these individual orbits, or the energies that the electrons in these orbits have would be better. Can an orbit have an energy? Yeah, that doesn't make a lot of sense. Okay, so I'm going to draw a big line here because this is kind of a breaking point.
Is that for neutral atoms? The calculation up there is different neutral atoms?
One proton, it could have potentially multiple electrons, I guess, but we're talking about 1 proton, 1 electron, the electron in different energy levels. So only for hydrogen. Let's see. So what about, unless there was a hand, nope, not one. What about energies for these orbits? And here we're going to break out a little bit more physics from earlier this semester. So energies, we know several different types of energy. Broadly speaking, we've talked a lot about potential energies and kinetic energies. Okay? So you might imagine we have a negative charge that is in the vicinity of a positive charge. We know something about point charges and potentials. We know how to get from potential to potential energy, electric potential energy. We're going to do that calculation. But also, if the electron is moving in this orbit, it's going to have a kinetic energy as well. So when we deal with the total energy, we're going to look at its potential plus its kinetic energy. So let's start and see if you remember the equation for the potential around a point charge. Anybody? There's a little more. You're like, I don't memorize anything. It's on my cheat sheet. Yeah, I understand. But you've worked enough problems. You would think like some of these kind of seep into your brain at some point. And then if they seep in, they should be able to leak back out. But maybe not. How about K, Q over R? All right, that's all. That's the potential created by a point charge. So we've got our point charge, which is the proton in the nucleus, and it's generating a potential around it, and the electron is sitting in that potential. Specifically, it's moving around in that potential, but we'll deal with that in a second. So if I want to say specifically for the proton in the nucleus, we could rewrite this as K, and we'll leave the R in the denominator. If we're looking at just hydrogen, then I'm just going to have E in this numerator. But specifically, let's not say hydrogen. Let's just say a nucleus in general at this point. And then there could be any number of protons, so we'll put a Z there again for the number of protons. So the potential around any given nucleus is going to be KQ, which is Z times E, over the distance R. What is that distance R? How does it relate to everything we've been talking about? Look above. Yeah, I think you know the answer. Right? It's how far it is away. Like it's where the electron is. That R in that equation is the R from above. It's these allowed orbits. That's the distance from the positive charge. So we're going to use that in just a second. Let's add to this, let's say, the potential energy for the electron based on this. Potential energy for the electron, U is what we've been using a little bit this semester for potential energy. Last semester we used PE, is going to be equal to Q times V. Which means if I'm dealing with an electron, the Q is negative E. So negative E times V. And then we can use this V equation from above. So we've got minus E, we've got minus KZ E squared over R. That's the potential energy that the electron has in some given orbit. We're going to use R sub n here in a second to specify which orbit we're talking about. So finally, if I want to look at the total energy that the electron possesses, we need to consider both its kinetic energy and its potential energy. So we could say E total is going to be the amount of energy that it has in a specific energy level or orbit. So I'm going to go ahead and put the subscript n on that. And it's going to be equal to its kinetic energy plus its potential energy. Surely you remember the translational kinetic energy equation. 1/2 mv squared. Yeah, that one was hiding in there. 1/2 mv squared. Good. And then we'll use from above our equation for the potential energy. So minus K Z e squared over r, and now we'll put Rn as our subscript. And at this point, a bunch of algebra happens. We're going to make two substitutions, and then I'm not going to do any of the algebra work, and you're going to go home and do it later, maybe. So, like half of you will have to be like, well, I need to see that it actually got there. And the other half of you will be like, I'm good. I trust that he did that correctly. So that's fine. Either way you want to go about it. So let's see. We're going to make two substitutions. First of all, for v. We had an equation for v above. It's equal to nh over 2 pi mRn. That was up there somewhere. I'm sure of it. Must have been on the previous slide. And we also had another equation for Rn. We said it was n squared h squared epsilon naught over pi mz e squared. And there are two Rn's once I plug in for that velocity. So yes, a lot of similar things in there, a big mess of stuff canceling out, things combining. I'll let you play with that. And let me scroll for a bit until we get to where we're going. Oh, also, don't forget k is equal to 1 over 4 pi epsilon naught, because I'm going to make that substitution. And eventually you're going to get this, that En is equal to negative z squared over n squared times m e to the fourth over 8 h squared epsilon naught squared. Blah. So if you merge all of these constants together, mass of the electron, elementary charge, Planck's constant, epsilon naught, the permittivity of free space, and then do a conversion from joules over into electron volts. So convert into electron volts, you're going to get this value. It's 13.6 electron volts. Remember that 1 electron volt is 1.602 times 10 to the minus 19 joules. So the number that comes out of there is in joules. Convert it into electron volts using that conversion, and you get a nice handy number, 13.6. I bet you've seen this 13.6 electron volts in a chemistry class. Yeah, okay. That is all coming out of physics we've done before, right? Several different physics concepts mashed together end up giving us this equation for the different energy levels of the electron and give us the common number that you see for that particular constant. So if we were to specify hydrogen here, we can do a few calculations. For hydrogen, again, Z is equal to 1. And the lowest energy level will correspond to N equal to 1. Which means that E1 is going to be negative 13.6 electron volts, which is the lowest energy level, so that's known as the ground state. And then higher energy levels are less negative, so E2 works out to be minus 3.4 electron volts, E3 is minus 1.51 electron volts, and so forth. Those are known as excited states. I like the term excited states. And there's something about it. Don't you just, you can just feel the electrons buzzing with energy. They're like, I can't believe this is happening. This is fantastic. I'm no longer stuck in the ground state. I'm excited. Do you ever feel that way in here? What if we had two windows? If we had two windows, would that raise you out of the ground state just a little bit? Maybe? Okay. Who's in the ground state right now? Anybody at E2? You feel a little, maybe higher than that? Higher than E3? 4? Ooh. Negative 1. Oh. This is getting a little bit scary. So, why these weird negative numbers? We need another page. Yeah, this never ends, apparently. I know. I'm sorry. Look at this. You're like, Out of pages. Can't do it anymore. I'm so sorry. So let's see. One more page here, and actually we're not even going to fill this whole page. One more thing. Why all the negative energies? That are approaching zero. Any thoughts? Why negative energies that are approaching zero? That seems a little weird. I hear something. What's happening out there? Do you have an answer?
Because there's lower energy when your increases and you get a negative.
What do you consider lower energy?
When N is big,
When N is big, that's not lower energy.
potential.
No? Well, lower potential maybe. I think you're getting close. Where is zero potential in this particular case? Infinity. Yeah, that's the key. We could say that V is equal to 0 and U is equal to 0 for R equals infinity. You might remember that's essentially the way we set up the potential around a point charge, right? If it's really close, R is small in the denominator, which means the potential is high. Remember those graphs that you all loved with the big peak in 3 dimensions that went out kind of flat as you get farther away? Okay, maybe you didn't love it. And we talked about the electric field related to it, and it was all just really beautiful. And you were all stunned, and you left here like, wow, that was amazing. I couldn't believe what I learned today. Maybe it's just me. Who knows? Well, all of that, right? It goes flat and essentially goes to zero if I'm very far away from a point charge, because it makes sense. If I'm nowhere near the point charge, why should it have any influence on me? Just like with gravity. If I'm very far away from the Earth, essentially I'm not feeling its gravitational impact anymore, okay? So V and U are 0 if I'm very far away. So that means that when the energy is 0, that's going to give me a barely free electron. In other words, it doesn't have any extra energy to move around, but it's also not being drawn toward the proton anymore, okay? There's not really an influence. If someone were to come along and say, hey, electron, bing, and just sort of flick it away, it'd be like, yay, I'm not trapped by that proton. It's free to go, okay? But it doesn't have any extra energy. If E is greater than 0 and we have a positive number, then we have a free electron with extra kinetic energy. So it's able to actually have some motion as well for a free electron with kinetic energy. One more asterisk on this slide. I know, it makes sense. You want to throw things at this point. I understand. The binding energy. Based on what we just talked about, the binding energy, or what is also known as the ionization energy, is equal to the energy to release the electron. Specifically the electron in the ground state. So based on the calculations we just did, the one in the ground state is at negative 13.6 electron volts. I need to get it up to E equals 0 to release it just barely. So clearly this energy is 13.6 electron volts for hydrogen. Okay? That is the end of that part of the derivations. Anybody have any questions, thoughts? Iced coffee? You're hiding it. Now it's floor iced coffee. Who wants floor iced coffee? Are there any other? You drank yours fast. Your question?
Where is the plastic energy supposed to be coming from? Where does that land on
It's not in them anymore. It no longer has an orbit. It has escaped that particular atom. And it has some kinetic energy. So some energy came from somewhere else and essentially broke the bond that it has electrostatically with the nucleus, and it's free to fly away. Anybody else? Anybody hiding behind me with a question? Seems like there's very few questions from the side here. What's that about? You say there's one over there? I kind of want to ignore them. Where are they? Middle or all the way on the other side? Can't tell? I don't see a hand. Oh, there we go. Which energy input into the system? It would have to be equal to some type of work that was done on the system. Yeah. Yeah. Your question. It's because of this equation. Let's rewrite it here. V is K Q over R. So when R is really, really big, V is equal to 0. And if you wanted to think about that in graph terminology, if I'm really close, V is high, but as I get farther and farther away, that has less and less impact on a nearby charge. Because V and U, the only difference is that we put in the charge. So Q times V is equal to U. The most potential is when it's as close as it can possibly be. When it's the most negative, it has the most, or excuse me, not that way. When it's the most negative, it has the least energy. And it takes it the most energy to get it out of there. I have to raise it to higher and higher energies in order for it to escape. I thought I heard something behind me. You dropped something. And I had to point it out. I'm sorry. All right. I think I can go to the actual next slide now. Okay? How does this, all of this, was there another hand? No, you're just scratching your head? Yeah, okay. How does all of this explain what we wanted it to explain? Remember, the point of all of this many, many slides ago now was that the Bohr model was supposed to explain those spectral lines that we see. And why, instead of just all of these colors of light being emitted, there's very, very specific wavelengths of light that get emitted. Well, it starts to make sense once I've restricted the energies that different electrons can have. And as it goes from one particular energy level to another, that is a discrete step. It can't just be anything. In other words, if I take a look at this particular graph, you see our 13.6 that's there, and the next energy we said was 3.4, and the next one is 1.5, and it continues. It is not possible for an electron to, say, have -9 electron volts. It just can't happen. It is not allowed based on everything that we just saw in those equations and what I'm going to show you later in today's lecture if there's time. It's not possible for, in hydrogen, an electron to have -9 or -5 or any of those other numbers. It's fixed on those discrete levels. So here's what we can say. If we excite an electron by adding energy, and maybe this is simply, say, from heat. So if we increase the temperature, that's one way to put energy. So maybe I've got some hydrogen gas, and I just decide to turn up the heat. Okay, I'm putting energy into the system. That will excite at least one electron. It will probably excite a bunch, but let's just assume we're going to look at one electron at this point. Now it's at a higher energy level, meaning maybe it was in the ground state, and it's like, whee, I've got more energy. I'm going to go up to this one. Now I've got that much energy, okay? Well, now you can imagine at some point it's going to cool back down. And as it cools, it releases energy in the form of a photon. As it cools, it releases energy in the form of a photon, and the only thing it can do is step between these different allowed levels. So if it excited up to n equals 2, then it's like, ooh, I'm cooling back down. It'll bounce back down to n equals 1, and what happens is, whoo, a photon comes and flies out of there of some given wavelength. So let's see how that happens mathematically. Oh, here we go with equation land again. Okay, so we have this equation for En. Let's see. So that is minus z squared e to the fourth m over 8 epsilon naught squared h squared times 1 over n squared. And we're looking specifically at hydrogen here. No, we're not. There's a z in there still. My bad. And we also had this equation that the energy of the photon is equal to HF, which is going to be the energy difference between some upper level and some lower level. It was one of the things we started the entire thing with. It's just that now I actually have an equation for those different energy levels. So we can make a couple of substitutions. We are going to take this thing and we're going to plug it in for both of those. And we're going to make a substitution for frequency. You might remember that it's related to the wavelength. So we're going to substitute in c over lambda for that. Frequency times wavelength equals the speed of light if we're dealing with light in a vacuum. If you do that, you get an equation that looks like this. 1 over lambda is equal to, let me see where I want to take this next step. It looks a whole lot like this. Z squared e to the fourth m over 8 epsilon naught squared h cubed c times 1 minus n for the lower state squared minus 1 over n squared for the upper state. And let me make sure that I wrote that down correctly. Otherwise, some of you are going to go home and try to plug that in and get to the answer, and then you're going to be frustrated for hours, and that would be sad. So z squared e to the fourth m over 8 epsilon naught squared h cubed c 1 over da 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 da. Okay. Now, if I look at two different energy levels, and I happen to know the n value for the energy levels that it's transitioning between, we have an equation that exactly predicts the wavelength of the photon that is emitted. And it turns out this equation works. It fits exactly what the experiments show us, both for the absorption lines and for the emitted lines. It works in both directions, and there's no problem with this. I'm seeing something here in my notes that makes me think I left out something previously, though. Let me scroll back. You're like, oh no, what did he do? What happened? Where is it? Did we have a big constant R somewhere that I completely missed? It's not there. It's not there. It's not there. Odd. Oh, there we go. Okay. So a couple of different things. First of all, this. We did have R. We had it last time. As long as z is equal to 1, that constant of all those things gives us R. The Rydberg constant that we had when we had that slide with all the different energy levels for the different series, the Lyman, Balmer, all of those happening. And keep in mind, this is the exact same equation we had before. And if you will allow me, I'm going to scroll back and prove that to you, I think. Let's see. So not that. Let's go back all the way to this slide. Looky there in the box. 1 over lambda is equal to R, and then I have 1 over some energy state squared minus 1 over some other energy state squared. Okay? Remember that this was just something that I gave you, and I said that plugging that in gives me all of those lines exactly. Now we see exactly where all of that comes from, and it comes from the Bohr model of the atom and a bunch of different physics that we've learned over 2 semesters. Be impressed. Okay, maybe not. I understand. It's nice how it all fits together, and some of it doesn't seem terribly useful, or useless, rather. Funny. So now that we have that equation, I should tell you that this is limited. right? The Bohr model, it works for some things, like we said at the start, but Bohr left out a lot. He specifies that, like, these electrons have one energy level, and now somehow they're in a different orbit and they have a different energy. It doesn't describe that process at all. Like, I mean, is it physically like, now I'm in a different orbit? Well, how did it get from point A to point B? What happened there exactly? Like, is it just like, I'm in an orbit and now I'm going to go, whoa, I'm in a bigger, like, what happens? There's no description of that at all. So that is completely left out. Also, we are assuming all of these circular perfect orbits, and we did all of the math based on that. And it fits experimental data for at least these experiments, but it's not true. And we've learned since then that the electrons aren't in these little perfect satellite orbits at all. It really doesn't behave that way. So what we can say about all this is that it's the Bohr model. It's simply one model that works partially, but by no means is it complete. And really, if you think about science in general, isn't that kind of the whole process all along? Right now, we have models of a lot of different things that work for some stuff, but you've got to know that there's coming experiments where it's like, our model didn't predict that. We didn't see that coming. And then the model has to be adjusted, and then we get a new model, and we continue the scientific process, okay? I think that is all that I want to say about the Bohr model. The Bohr model. Maybe it should be respelled. Maybe. I don't know. Perhaps. Any questions, thoughts? Anything? No? Nothing at all? Okay, so let's jump over to this other set of slides. I want to do a couple of these, and then we'll be done for the day. And we can finish up this chapter and hopefully do a little quantum physics on Friday before we do relativity. All next week. Yay, relativity. It's going to be a good time. You have no idea what you're in for and how much fun it's actually going to be. Yeah, I know you don't believe me. So, I think this is pronounced de Broglie, maybe? You think de Broglie? That's how I would say it. I don't think it's de Broglie, though, is it? You've heard it pronounced in some other class. Is it not de Broglie? You have no idea, do you? No? Have you seen the guy's name before? You have. But it's one of those where you see it in print, and you pronounce it some way in your head, but you never say it out loud. And then you end up in front of a class teaching people realizing like, oh, wow, I've seen that word for 30 years, but never had to say it out loud. Now how do you say it? And then you're in the position I am right now. Sad. I think it's de Broglie, but I like de Broglie just because it's very literal, and I like to say things in a very literal way. De Broglie's matter waves. And right now there's some physicists at the door thinking like, what's wrong with him? Why did we hire that guy? He's just not pronouncing the person's name right. I knew him. One of those kind of situations. So, de Broglie's matter waves. Here was the thing that this guy said. He liked symmetry in nature, and we've seen this an awful lot. The idea that if light had already been shown to behave sometimes like a wave and sometimes like a particle, well then why can't particles be both as well? It seemed to make sense that if one thing was true, the other should be true. So the hypothesis here is that maybe particles sometimes act like waves. Maybe particles sometimes act like waves. When we looked at the double slit experiment, I mentioned that it worked with electrons as well. So we already know that there are experimental results that show that particles do exhibit wave-like behavior. But we didn't deal with that at all analytically or say where that came from. So here is what these matter waves and this hypothesis says, is that for all particles with energy and momentum, this equation is true, or these two equations. First of all, E is equal to HF, just like we had with photons. So we're going to say that that is also true for electrons or any other piece of matter. And that the wavelength of these particles, which all of a sudden starts to sound weird, right? The wavelength of an electron, that starts to kind of mess with the head a little bit, is equal to Planck's constant over the momentum, P, the momentum, if you remember last semester, right? Yeah, half of you weren't in that class, so you have no idea what's going on. So this could be the classical linear momentum, And P is equal to what? Good, thank you, MV. That one came fast. Or, and I'm going to use a term that we don't really know anything about yet. We'll learn about it next week. Or it could be the relativistic momentum. And for that, see next week. All right, just for now, I just want to point out that it's valid for both. This thing is known as the de Broglie wavelength. It's not his wavelength, though, you know? It's not like it's de Broglie's wavelength of particles, I guess one might say. So, if you're thinking like, okay, fine, mass, matter, things have wavelengths, whether it be an electron or an iPad or the person who teaches, you know, whatever. Everything has a wavelength, even if it has mass. As long as it has energy and momentum, keep in mind, if all of a sudden I decide that that's going to be zero, then that equation just falls apart. It's completely undefined at that point. If it has no velocity, it has no meaning physically at all. So why don't we just simply do some calculations, like for a macroscopic item? Let's say maybe, for example, just a ball. We're going to give this ball a mass of 0.2 kilograms, and we're going to let it have a velocity of 15 meters per second. That seems like a regular occurrence that one might deal with. Let's figure out what the wavelength of that would be. So that's h over p, which is h over mv, which is 6.626 times 10 to the minus 34. And in the denominator, we have 0.2 and 15. This wavelength is depressing. Very, very depressing. You will get a wavelength of 2.2 times 10 to the minus 34 meters, which might make you question whether any of this makes sense at all. 10 to the minus 34, atomic level things, angstroms, 10 to the minus 10. Like, we have no way to experimentally deal with sizes that small. Not even close. Orders and orders of magnitude away from that, which means that this might as well be in the realm of science fiction, right? It's like, fine, make it up. Who cares? Like, you calculated it, great, good job, all right? The thing is that as the item gets smaller, you start to see interesting things. So don't take this to say like that you don't have a wavelength. You do. If you're moving, it's just really, really small, okay? So it might as well not exist. It doesn't affect you in any way. Don't worry about it. But if we were to deal with a microscopic item, and we'll end with this, like an electron. And let's say it's an electron that is accelerated from rest through a 100-volt potential difference. So lest you think that the velocity we're going to use is something completely ridiculous, 100 volts isn't a big deal, right? 100 volts kind of all over the place. We deal with 100 volts all the time. Using 100 volts to accelerate the electron, meaning like we're going to put it in this potential difference in the direction that it wants to go, and it's like the 100 volts is going to make it accelerate. We could say that its kinetic energy, 1/2 mv squared, is going to be equal to E times V, where V is that 100 volts. And if you solve that for little v, the velocity, you're going to get 5.0, what is that number? I think that's a 9. See, my handwriting causes me problems as well. Times 10 to the 6 meters per second. So yeah, that's a lot of velocity, but it doesn't take much to accelerate something with that small of mass to a really high velocity, okay? So it's not a ridiculous velocity that we're considering. If you then plug that into the equation above, lambda is h over mv, you're going to get 1.2 times 10 to the minus 10 meters, or 0.12 nanometers, all of a sudden we're on the order of the spacing of atoms in a molecule or in any other bulk substance. That wavelength is not insignificant. Okay? If you imagine being an electron hanging out with other electrons, ooh, what is that world like? That's not like me and you, right? Our wavelengths were like, fine, you have a wavelength, I can't see it. If you're an electron hanging with another electron and you both have a wavelength that's, like from here to the wall and you're like the size of me, it's like all of a sudden it's like, I see your wavelength. How is this going to affect how we interact with each other? We're going to wake up. Class is over. Goodbye. That was like right at 4 o'clock. Good job. Was that you? I don't know. Yeah, okay. You woke us all up. We're good. We'll talk about that more on Friday. I will see you then. Goodbye. Here's where we were. De Broglie or de Broglie, depending on how you like to read. Proposed this idea of particles sometimes acting like waves and said that all particles that have energy and momentum, in other words, they're moving in some fashion, are going to fit these two equations. The energy looks a whole lot like the energy we had for the photon, so it's dependent on the frequency, and then we can calculate a wavelength that involves Planck's constant and our regular old momentum, mass times velocity, or other types of momentum that we haven't learned about yet, okay? So we kind of worked through this, just talked about the concept. We did a couple of calculations so you can get a feel for how big these waves are. And we start to see that the size of the waves, the wavelengths for larger objects really don't matter. Are they not there? No, they're still there. We just can't really see them and detect them. We can just do calculations, all right? As we start to deal with smaller and smaller and smaller and more microscopic things, all of a sudden the wavelength size starts to become reasonable. At least it's on the order of things that are interacting at that level, which means that those wavelengths are going to impact each other in ways, and it makes you kind of wonder what things would be like if you were down on that level, interacting with things where you had a wavelength and they had a wavelength, and you can kind of see that wavelengths are happening, and life would get a little weird, all right? Now, one thing we didn't do, and I've got another slide for this, is to make this connection back to things that we've been talking about. We could say that this idea basically filled in the theory that was missing from Bohr's quantum condition previously. We'll say that Bohr was missing. And I'm going to show you how that works. And that will essentially be the end of serious things in this chapter. We're going to rush right through the remaining slides. This fills in the theory that Bohr was missing. Now, I have to give you a little bit of background from a chapter that we don't cover in this class. And once again, it's kind of coming back to haunt me at this point, because we didn't do a serious study of waves and simple harmonic motion and all of this sort of stuff. There's a little bit of theory that you're missing, and I'm going to try to give you a really, really brief overview and show you a video that's going to help you understand this stuff. Standing waves on strings. Whoops, I left out the word waves. That's the important word. Standing waves on strings. Before I get to the video, does anybody know what I'm talking about at all? Standing waves? Strings? You know what a string is? Wow, you don't even know what a string is? Yes, exactly. Attach a rope to the wall. Thank you. And I'm going to, well, don't attach a rope to the wall. Imagine a rope attached to the wall. I'm going to hold this end and hold it rather tight so it's stretched out, and then start doing this to the rope, okay? It's a chemistry thing. It kind of is. All of this kind of goes to chemistry a little bit. So imagine doing this, and I'm creating the bumps in the waves, and they travel down, and they hit the wall. And remember, we learned something about when it hits the wall, it flips upside down, and then it comes back. And so I keep sending waves this way, and waves are reflecting back, and I'm sending more waves. You might imagine that if I time it just right, when the wave is coming back and it's inverted, and then there's peaks and valleys and peaks and valleys, if my new wave is timed just so, I might be able to get my new peak to line up with the peak that's coming back at me, and we could get constructive interference. Can you imagine that at all? All right? No, you can't. Yes, you can. I know you can. I think you can. All right? So imagine waves are going out, they're bouncing back, and I have a frequency that I'm oscillating this into the string that matches just perfectly so that all of the peaks going that way and the ones coming back are lined up, which means that even though there's all these waves traveling back and forth, it looks like nothing's happening. In other words, like the peak that's lining up right here, it appears that it's just sort of stationary. In other words, standing on the string. It's perfect constructive and destructive interference where I have all of these bumps and valleys that are all just perfectly lined up. And let me show you the video of what this looks like, and then it will help with everything, I think. We are not going to watch the entire video. Instead, I want to show you just a little piece. I'm going to have to drag through until I see what I want. And you can't see anything yet. Ooh, I can see the little preview to find what part I want. I think it's right here somewhere. I don't know what I'm doing. No, that's not it. Hold on. We're going to find it. It's too long. Ooh, maybe right there. Let's see what this does. Come on, Internet. You can do this. Yes, talk amongst yourselves. It'll be fine. I didn't want you to watch this anyway. Go a little farther. Try again. Go back. Nothing works. None of you care, do you? You do? Are you sure? Oh, man. Come on. Because I have a second video I want to show you, too, and it's even more important. Why is it not working? I'm connected. That's good. Nothing's working. Absolutely nothing. Oh, something appeared briefly. Let's just wait for it to load completely, and then I'll drag it around. How's everybody doing today? Are you good? Are you happy? Can you tell me if something appears up there? Yeah, you will? You promise? I'm just going to give it like 15 seconds without trying to drag around the little slider. Has anything happened yet? No, not yet. You really want to see what's going to be up there, though, don't you?
Yeah.
I thought so. It's making me sad. It usually works. Why not today? Well, I shouldn't put my faith in it? No? I'll create my own additional waves. All right. Never mind about that for now then. Let's just go back to this. Apparently it's not going to work. What are you going to do? All right? Standing waves on strings. I think that at least maybe you can feel what the idea is. Are you okay with the idea? Hello, you out there now? Or did I lose you completely? Yeah, you're back? Okay. Standing waves on strings, we could say that based on how fast I'm oscillating this up and down, that's going to correspond to a certain length of a wave such that only certain wavelengths will work. Certain. Or in other words, will fit, you might say. I need the wavelengths to be just so between the distance I am between me and the wall so that they perfectly fit in there. In other words, if I were to draw a diagram of these standing waves, maybe here's the wall, and let's just say that I'm a wall too. Why not? And then maybe I'm going to draw some waves in here and watch this like kind of not work out. Oh, that did. And then I'm going to draw the opposite version of those. Ooh, like so. Yeah, not too bad. All right. This is kind of what it would look like, except you can imagine in these regions it's sort of oscillating up and down, but so fast that you can't really see it go up and down. All you see is like, ooh, there's a peak in a valley, and I see it just standing there. All right? Notice the way that I drew this, that, well, this end is attached to the wall, and this end is attached to my hand. And you can see there's two full wavelengths that are there. Exactly. I can't have like 2.26 wavelengths. They don't fit. In other words, I've restricted what wave will fit there. Now I could, on the other hand, like go and maybe hold the wave here and oscillate it. That'll work. I can go here and oscillate the wave, and that'll work. I can't like go right here and have one full wave and then like a little piece of a wave. It doesn't work. If I do any of those other ones, standing waves won't be created, and we'll just end up with a string that's just kind of going, like that. It'd just be kind of ridiculous, not orderly, nothing's going to work. There would be this weird mixture of destructive interference where nothing's working well, okay? So in other words, since I can go to any of these like half wavelength locations and make it work, we could say that the length of the string must be equal to k lambda over 2. So some integer multiple of a half wavelength, and we're going to let k equal 1, 2, 3, and so forth. Only certain wavelengths will work. Let me add a couple of notes here just for completeness. You could say that the ends are fixed boundaries. Fixed boundaries. And I think that's about all that I want to say about that. Now, to get this to correspond somehow to the atom and the electron, which right now it seems like it's completely far apart, what if instead of a string that was straight between here and the wall, I wrapped it into a circle so that we're going to make it match the situation that the electron is in. It's in a circular orbit, and we're trying to say that it's not a particle, but a wave that's fixed into this circle of a certain radius, okay? If you were to do that, so let's see, wrap it in a circle. A couple of things are going to happen. First of all, if you imagine taking what we have up there right now with 2 full waves and wrapping it into a circle, all of a sudden I start to, you can see that it's still going to fit because I have, again, the end conditions are matching up perfectly. On the other hand, if we had a situation where maybe it was 1.5 waves, which works if it's straight, that's fine. But if I wrap it into a circle, then it's like I've got 2 peaks that are next to each other. That wave doesn't fit all of a sudden. All of a sudden I need a peak and a valley and a peak and a valley. We have to have them alternating, which means that I have a condition now where only full waves are going to fit. Once I wrap it into a circle, I have a new restriction. So let's add to this, wrap into a circle, and only full wavelengths fit. Which means that I'm going to redefine k. So I'm going to say now that k is not just any integer, but it's equal to 2 times n, where n is equal to 1, 2, 3, and so forth. That's going to give me even integers, which creates full wavelengths instead. And now, what is the length if it's wrapped into a circle? The length is the circumference, so that's 2 pi r, okay? Believe it or not, this is going to go somewhere, and when we're done with it, you're going to be like, oh, and you're just going to pass out with delight. And you're like, physics is the most amazing thing ever, and then you're probably going to want to take your banana and just throw it in the trash. Why? Why are you doing this to yourself? Look at all the faces around you. They're all like this. Look at them all. Look, those are smiles. Stop. Stop the smiles. Why are you smiling? No, I know what you're really thinking. It's disgusting, isn't it? Don't you hate every flavor that you have right now? No, you don't. You don't like it. You do not. Stop talking. All of you just stop talking. I can't take it anymore. All right, so we're going to take this, and we're going to plug this in over here, and we're going to take this k, and we're going to plug it in there and get a new equation. Oh, I'm so disgusted right now. It's just the worst.
With a banana-colored shirt on.
I know. That repels other bananas. I think. I have no idea, actually. So let's see. Now I've got, what in the numerator here? 2n lambda over 2. So the 2's cancel. So we've just got n lambda there. And then we can solve that for lambda. So we've got lambda is 2 pi r over n. Do I need to tell you what I just did again, or are you just copying stuff down? Yeah?
Yeah.
So we switched it into a circle, which made us do two substitutions. First, K is now going to become 2N to force full wavelengths instead of allowing half wavelengths. And now, since the length is a circle, I can say it's the circumference, 2 pi r. And we're going to plug those into the equation I had previously. Yeah. Odd numbered Ks are going to give you half wavelengths, yeah. Yes. A half of a wavelength would work, but no smaller. Question?
What do K and A represent?
I'm just trying to get some integers in here so I can represent half wavelengths and whole wavelengths.
Okay, so if K represents the number of wavelengths, then
K is just integers.
and N too?
And N is now just integers.
Then what does K equals QN represent?
Nothing. Really nothing. It's just a way to say, plug those in and we're going to have 1 lambda, 2 lambda, 3 lambda, 4 lambda, and so forth. It's just a way to count.
And your denominator, so when you use that equation, what do you plug in?
You plug in all of these. So you've got an infinite set of equations, really. Okay? All right. Now let's use this with something we had before. All right? We're going to take this. This is our new restriction on lambda, and we're going to say from before we had these two equations. Lambda is equal to h over p. That's our matter wave equation. That's the de Broglie wavelength. And we're going to take what we just had and plug it in. So now I've got 2 pi r over n equals h over p. And then we're going to solve that for momentum. So momentum is equal to nh over 2 pi r, which means we are one step away from what I really wanted to show you. Okay? Let me rehash just a little bit. Right? We're using the idea of standing waves wrapped into a circle to model an electron as a wave that's restricted into a circular orbit. Okay? By doing that, we now have an equation for wavelengths that fit into the circle, and we're plugging that into our equation for the de Broglie wavelength, which was the whole hypothesis to begin with. Okay? Once we have that, we're now going to go back to Bohr, good old Bohr, and use the angular momentum. L is equal to RP, and I'm going to plug in for the momentum we just found. So this is the angular momentum of an electron in a circular orbit. And now we have R in H over 2 pi R. The R's cancel. And L is equal to NH over 2 pi. Where have you seen that equation before? We specifically called this Bohr's quantum condition. Remember, there was that equation that he just made up because it worked? That's it. Except this time, we actually have some physics that leads to it that makes a little bit of sense. This fills in the theory a bit and gives him a little more backing and makes it more reasonable. Yeah?
Because we're just looking at the angular momentum, does that mean that we're ignoring linear momentum to propagate the wave?
Well, keep in mind they're interrelated. So at each instant, you could think of the electron as having linear momentum, but it keeps changing direction so that L equals RP. It has the linear momentum in there, but it's like a component of the overall angular momentum. So it's not like we're totally leaving it out, but because it's moving in a circle, we're focused on the angular way of expressing it. Okay? That is the end of this. Do you have questions, thoughts, complaints? You want something new and different? Yeah, I thought so. Okay? So, de Broglie matter waves, these slides I'm not even going to talk about. Yes, I am, just a little bit, okay? Two different diffraction patterns. Let me just point out that the one on the left was done with X-rays. That's an electromagnetic wave. And the pattern on the right was done with electrons. This just adds fuel to the flame that electrons or particles behave like waves as well. Just like with our two-slit experiment, doing actual electron diffraction experiments where we send electrons or X-rays in, we get essentially the same result, the same type of patterns come out of that. We can even build microscopes with electrons. What we know about microscopes up till now is they're an optical thing with lenses, light rays that go through. It turns out we can have a very similar thing with electrons where we're using the electron waves and we refocus them using magnetic field lenses, if you want to think about it that way. It's perfectly analogous, and it allows us to see things that are much, much smaller because the wavelength of an electron is much smaller than the wavelength of light, right? We're talking 10 to the minus 10 instead of dealing with 10 to the minus 9. That's a whole order of magnitude in difference. So you're seeing something that's much, much smaller. There's some pictures. Aren't they beautiful? Yeah, that's nice. That's pollen on the bottom left. Sneezy, sneezy. All right? Yeah. And pollen. That just kind of makes you want to sneeze, just looking at it. Right? Imagine, all that gets up in your nose, you know, and then, so the next time you sneeze, I want you to think about that. Yeah, tickles in there a little bit, right? And then up here, some other electron micrographs. We can see things that are way smaller than we'd be able to with just light by itself. Which brings us to the last slide, and this is only going to serve the purpose of taking us to Chapter 7. Wave-particle duality has really been the focus of many slides now, right? We're talking about the fact that both particles themselves and light waves act like the other thing. All of them have experiments that show us that, well, sometimes it's a wave, and other times it's just like it's a little particle that's moving around. And there's this thing that really can't be reconciled. And really, even to this day, there are no conclusive answers. We get results that disagree with each other, and we kind of just have to go with whichever theory seems to fit the experiment or the project that we're currently working on. There are no conclusive answers, which is a problem. So, what we have to do is develop something completely new known as quantum mechanics. Sometimes you'll just see this called physics, quantum physics. They're both the same thing. Quantum mechanics sounds fancier, though, don't you think? Yeah, just a little bit. Mechanics, you might remember, is really the first part of Physics 8A that we did, all the stuff with Newton's laws and kinematics and all that stuff. That's essentially mechanics that we did last semester. This is just the quantum version of it. So it's like quantum introductory physics. I don't know. That started to sound like a bit of a contradiction.